Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Part 16. Equation Derivation Rules. How equations fall out of the cost story. Remember the language we are learning. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we listen to just one of those echoes. You are walking the fertile paths of Book 9.4 in Episode 9, the generative grammar. Our entrance into dynamical grammar has been transformative. In Part 15, we encountered the core organizing principle, the action SFA, a cosmic cost function that grades entire histories of the phi field. We learned that the universe prefers to tell stories, to actualize histories, that make this action stationary, most often minimal. It chooses the cheapest narrative. This answered the profound why of dynamics. But a pressing question remains. How, in practical terms, does this abstract preference for minimal cost translate into the specific, detailed rules of motion we observe? How do we get from the global philosophical statement, nature minimizes action, to the precise, local equation that tells a planet exactly how to curve through space at this instant? Today, in Part 16, Equation Derivation Rules, we uncover the mechanical bridge. We learn the precise grammatical procedure that takes an action S and extracts from it the equations of motion. These are not separate laws. They are necessary consequences. Our anchor image is a master stonecutter at work on a nearly finished marble statue. The block is gone. The rough form is there. Now, the sculptor makes the tiniest, most delicate taps with hammer and chisel. She's not reshaping the whole figure. She's testing and refining the surface. At the moment the statue is perfect, when it matches the vision in her mind, any tiny tap in any direction would slightly mar the perfection. The perfect form is stable against infinitesimal variations. It is a point where the cost of being off vision increases no matter which way you nudge. The actual physical history of the phi field is like that finished statue. The action S is the sculptor's vision of perfection, and the equations of motion are the mathematical expression of that stability. The condition that says, at this point in the story, any tiny allowed change to phi's configuration will make the total cost S increase. Today, we learn the chisel and hammer of dynamics, the calculus of variations, leading to the Euler-Lagrange equations. Here's the precise puzzle of this part. We have a number, S, that depends on an entire story of phi. We want to find the specific story that makes S stationary. We can't just guess and check infinite stories. What systematic procedure can we follow that, given the formula for S, inevitably leads us to a differential equation that the winning story must obey at every point in space and time? The answer is a beautiful piece of mathematical grammar called the principle of stationary action applied through variation. Let's walk through it step by step with our ears, not our eyes. First, imagine you have a candidate story, a specific history of how phi evolves over time and space. Call it phi actual, Tx. Now, imagine creating a tiny arbitrary wiggle or variation on top of this story. At every point, you change phi by a minuscule amount, which we can call delta phi. This delta phi is like the sculptor's tiny tap. It's zero at the start and end of the story, we fix the boundaries, and it's smooth, but otherwise it can be any small shape you like. This gives you a new, slightly different story, phi actional plus delta phi. Second, you compute the action S for this new wiggled story. Since the wiggle is tiny, the change in the action will also be tiny. We call this tiny change delta S. Third, and this is the crucial logical move. For phi actual to be a stationary point of the action, this delta S must be zero for every possible tiny wiggle delta phi. Not just some wiggles, but all conceivable infinitesimal deviations. If there existed even one specific tiny wiggle that could lower the action, then phi action wouldn't be at a minimum. You could improve, cheapen the story by wiggling it that way. If a wiggle could raise the action, that's fine for a minimum, but the condition for stationary, which includes minima, maxima, and saddles, is that the first order change is zero. So delta S equals zero for all wiggles. Now the magic. The action S is an integral of a density. Let's call it the Lagrangian density L, which depends on phi and its derivatives, phi's rate of change in time, omega, and its spatial gradients, k. When you carefully calculate what delta S must be for it to vanish for all possible delta phi, a specific condition is forced upon phi acting Ederker. This condition is the Euler-Lagrange equation. For our audio understanding, we can state its essence. For the action to be stationary, the rate of change in time of the derivative of L with respect to omega, plus the spatial divergence of the derivative of L with respect to k, must equal the derivative of L with respect to phi itself. Let's unpack this mouthful. It is a precise balance sheet. It says, the cost tally L has sensitivities to how fast phi changes, omega, how unevenly it's arranged, k, and its base value, phi. The equation demands that these sensitivities balance each other out in a very specific way, locally, at each point in spacetime. This local balance condition is the equation of motion. It is the condition that ensures no tiny local wiggle can, when integrated over the whole story, change the total cost. So the procedure is, write down the actions phi based on the physics of the system. This encodes the cost of kinetic versus potential effects. Insist that S is stationary against all tiny variations. Out pops the Euler-Lagrange equation, which is the equation of motion for phi. For a single particle, this yields Newton's second law, F equals ma. For the electromagnetic field, it yields Maxwell's equations. For the gravitational field in general relativity, it yields Einstein's field equations. The equations are not primary, they are derived. Let's listen to the triunity of this derivation process. The time echo of derivation, the localization of global judgment. The action principle judges the entire history. The Euler-Lagrange derivation translates that global judgment into an instant-by-instant rule. It says, if the whole story is to be optimal, then at this moment, the relationship between phi, omega, and k must be this. It turns a holistic, almost teleological condition into a causal differential equation that can be integrated forward in time. The time echo is this crystallization of global constraint into local law. The future is not pulling the present, but the requirement of overall optimality forces a specific rule on the present's behavior. The space echo of derivation, the balance of internal stresses. For a field, the Euler-Lagrange equation is a balance of stresses. The term with the time derivative of dl d omega is like an inertial term, resistance to change in time. The term with the spatial divergence of dl dk is like a pressure or tension term, the cost of spatial unevenness pushing back. They balance against the force term, dl d phi, which is the cost of being at a particular phi value. The space echo is this detailed force balance at every point, a microscopic condition ensuring that no tiny rearrangement of the field's spatial profile could lower the overall cost. The motion echo of derivation, the prediction of trajectories and waves. Once you have the equation, you can solve it. For a particle, solving gives the trajectory x of t. For a field, solving gives wave solutions, dispersion relations, and packet evolution. All the things we studied in book 9.3 now find their ultimate origin here. The motion echo is the computational power released by the derivation. The abstract stationarity condition becomes a tool for predicting specific testable motions. The orbit of Mars, the vibration of a guitar string, the path of a light ray. Now let's locate this procedural node on the master tree. We are on the equation derivation branch, the first major limb of the dynamical grammar trunk. This branch depends directly and absolutely on the parent node of the action SFA as the fundamental selector. Without an action, there is nothing to vary. It enables the next critical nodes, symmetry and conservation laws, Noether's theorem, which arise from properties of the action and its resulting equations, and nonlinear interaction rules, where the Lagrangian density L includes terms that couple phi to itself, leading to complex interactive dynamics. This branch is where the grammar becomes computationally actionable. To ground this powerful abstraction, let's illuminate our path with lanterns. A near lantern from cooking, finding the perfect soup temperature. Imagine you are simmering soup. Your action is a cost function combining two desires. You want it hot, close to a target temperature T target, but you also want to avoid using too much gas, high burner setting. Let phi be the soup temperature, omega its rate of change. A simple Lagrangian could be L equals 1/2 times omega squared plus 1/2 times phi minus T target squared. The first term penalizes rapid temperature changes, wasteful gas flicking. The second penalizes being off target. The Euler-Lagrange equation derived from this is the second time derivative of phi equals minus phi minus T target. This is the equation of a harmonic oscillator. It tells you the optimal burner adjustment strategy. If the soup is too cold, phi T target, you should be increasing the temperature, positive omega, at a rate proportional to the gap. It leads to a gentle, oscillatory approach to the perfect temperature without overshooting. The equation of motion for the soup falls out of your stated cost of operation. A middle lantern from engineering. Designing a suspension bridge. The cables of a suspension bridge under load take a specific shape, a catenary. Why this shape? It is the shape that minimizes the total potential energy of the cable. The action is the integrated gravitational potential energy. Applying the principle of stationary action, here minimal energy, to the cable's curve leads to a differential equation whose solution is the catenary. Engineers don't guess the shape. They derive it from the minimization condition. The equation governing the curve is a direct consequence of the cheapest configuration under gravity and tension. A far lantern from quantum field theory, the Dirac equation. This is the fundamental equation describing relativistic electrons and other spin 1/2 particles. It was not guessed. Paul Dirac sought a relativistic version of the Schrödinger equation that was linear in time and space derivatives. He derived it by demanding that the square of his desired equation yield the correct relativistic energy-momentum relation. This demand is essentially a stationarity condition on a more fundamental action. The beautiful, profound Dirac equation, which predicted antimatter, fell out of a requirement of internal consistency, Lorentz invariance, in the action-based framework. The equation is a consequence of a deeper grammatical constraint. From soup temperature to breach cables to the equation for antimatter, a universal theme. Optimality or consistency conditions, when expressed mathematically as the stationarity of an integral quantity, generate specific, often elegant differential equations that govern the system's behavior. The equations are the footprints of the optimization. What then is the specific language role of equation derivation rules? They are the grammatical inference procedure. They are the set of syntactic operations, variation, differentiation, integration by parts, that allow us to deduce the necessary local conditions, the equations, from a global declarative statement, the action principle. It is the logic that moves from stating a rule about entire narratives to generating the rules that govern each sentence within them. The core question this part asks about phi is, given a specific form for the action cost functional S phi, what are the necessary and sufficient local conditions, differential equations, that a phi history must satisfy in order to be a stationary point of S? We are moving from the declarative, minimize this, to the imperative, at each point you must obey this. What does this derivation procedure do in the generative process? It translates a global selection principle into local, solvable differential equations. It unifies the derivation of all fundamental equations of physics under one common method. It ensures consistency. The derived equations automatically respect the symmetries built into the action. It provides a systematic recipe for moving from a postulated cost to testable dynamical predictions. Now, stability and breakdown. The Euler-Lagrange derivation is a mathematical theorem within the calculus of variations. It is exact and rigorous given the assumptions: smooth functions, fixed boundaries, and an action that depends only on phi and its first derivatives, or higher in generalized versions. It breaks down or requires modification if the system has non-holonomic constraints, constraints on velocities that cannot be integrated to positions, or involves dissipative forces like friction in a fundamental way, as these cannot be easily derived from a simple time-symmetric action without extending the framework. Within its vast domain, virtually all of fundamental conservative physics, the procedure is ironclad. This brings us to our unwavering commitment: falsifiability. The claim that equations of motion derive from an action via the Euler-Lagrange procedure is not a tautology. It's a structural hypothesis about physical law that makes stringent predictions. The central claim: for a system described by a holophase field phi, once the correct action S phi is identified, the equations derived via the Euler-Lagrange procedure must accurately predict the system's dynamics. This includes 1. The full-time evolution from given initial conditions. 2. The linear response, small oscillations, normal modes, around equilibrium states. 3. The stability thresholds, predicting when a small perturbation will grow or decay. A concrete measurement scene, the simple pendulum. Consider a simple, ideal pendulum, a mass on a massless string. Its dynamics are famously governed by the equation the second time derivative of the angle theta plus Gems for liter times the sine of theta equals 0, where g is gravity and L is length. Our claim is that this equation derives from an action. The action is the time integral of kinetic tally minus potential tally. S equals integral of 1/2 times m times L squared times omega squared minus mgl times 1 minus cosine of theta dt, where omega is the angular velocity d theta dt. We set up a precision pendulum experiment. We measure L and G very accurately. We release the pendulum from a known small initial angle, say 10 degrees. Using high-speed video, we track the angle theta t with high temporal resolution over many swings. The pass condition, validation. The recorded trajectory theta t matches the solution of the Euler-Lagrange equation derived from Rs. For small angles, the equation linearizes to a simple harmonic oscillator, predicting a period t equal to 2 pi times the square root over lines over jam. The measured period matches this. For larger release angles, the period lengthens in a specific predicted way due to the nonlinear sine term. The detailed shape of the theta t curve, its anharmonicity, also matches the numerical solution of the full nonlinear equation derived from S. The dynamics are fully captured by the equation that fell out of the action. The fail condition, falsification. The pendulum's period for small angles systematically deviates from 2 pi times square root the length over jam after all known corrections, air resistance, string mass, finite amplitude, are accounted for. Or, the large angle anharmonicity follows a different functional form than the one predicted by the sine term in the Euler-Lagrange equation. Most tellingly, if we derived a different equation from a different, plausible-looking action, say one with a cosine potential instead of 1 minus cosine, and that different equation fit the data better, it would falsify our original action. It would show that the cost story we thought governed the pendulum was wrong. The link from a specific S to a specific equation to specific data is a tight chain that can be broken at any link by experiment. This falsifiability ensures that the elegant mathematical bridge between action and equations is constantly tested against the reality of swinging pendulums, orbiting planets, and propagating light. Let's cultivate a practical recognition skill. You can train your mind to see this derivation logic in any scenario where a best or most stable state is defined by an optimization condition, and where that condition leads to a specific rule that must be satisfied locally. Watch a hanging chain or cable. Its catenary shape minimizes potential energy. If you imagine pinching a tiny segment of the chain and moving it up or down, you would increase the total energy. This local no benefit to moving condition, applied all along the chain, translates into the differential equation of the catenary. Observe the layout of a garden irrigation system. If the goal is to minimize total pipe length while connecting all sprinklers, a classic Steiner tree problem, the optimal layout has a specific property. At any junction where pipes meet, the angles are typically 120 degrees. This geometric rule is the equation of motion, derived from the minimization of total length. You could find it by imagining wiggling the junction point and seeing that any wiggle increases the total length. Consider portfolio rebalancing in finance. Given a utility function, a kind of action combining risk and return, the optimal portfolio satisfies the Euler-Lagrange type condition that the marginal benefit of shifting funds from one asset to another is zero. This condition generates the equations of modern portfolio theory. Whenever you encounter an optimization problem whose solution is characterized by a local condition of no first-order gain from tiny changes, you are seeing the conceptual kernel of the Euler-Lagrange derivation. You are seeing equations as stability conditions. We must connect this procedural bridge deeply to our holophase journey. In the previous part, we found the director, the action. Now we have learned the director's method of directing, by enforcing a local balance condition, the equation, at every moment that ensures the overall performance, the history, is optimal. The waves, packets, and interference patterns of Book 9.3 are solutions to the equations derived from appropriate actions. The grammar is now fully operational. We can start from a principle, minimize this cost, derive an equation, and solve it to generate the predicted stories of the universe. If you want to see the full mathematical derivations and exact equations behind this idea, The detailed steps of the calculus of variations, integration by parts, the functional derivative, and the general form of the Euler-Lagrange equation for fields, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Let us pause and feel the solidity of our position in Book 9.4. We have moved from the declarative principle of least action to the operational machinery of equation derivation. We now possess a complete engine. Postulate a cost, action, apply the derivation rules, variation, obtain the equations of motion, Euler-Lagrange, then solve or analyze them to predict physical behavior. This is the core method of theoretical physics. In the next part, we'll discover one of the most beautiful gems revealed by this structure, Noether's theorem. We will learn that if the action S remains unchanged under a continuous transformation, like shifting in time, space, or rotating, then the corresponding Euler-Lagrange equations imply a conservation law. Symmetry in the cost function yields permanence in the story. Time translation invariance gives conservation of energy. Space translation invariance gives conservation of momentum. This profound link between symmetry and conservation will emerge naturally from the grammatical structure we've just built. Before we end, the mandatory zoom out to hold our scope. The Euler-Lagrange equation, for all its power, is still just a condition on phi and its derivatives, derived from the action S, which is itself built from phi and its derivatives. We have added no new substances. We have simply unveiled the logical consequences of the stationarity requirement. One field, phi, plus its infinite tower of derivative questions, plus the principle of stationary action, plus the rules of variation. From this, the specific deterministic laws of motion are born. The universe's storytelling is both free, choosing the cheapest path, and bound, rigorously obeying the local condition of that cheapness. As we conclude, hold the image of the sculptor and the nearly finished statue. Her final, perfect form is stable. A tap here, a tap there, only makes it worse. The equation of motion is the mathematical expression of that stability at every point on the statue's surface. The universe is the sculptor. The action S is her ideal. The evolving phi field is the emerging statue. And the equations of motion, Newton's, Maxwell's, Einstein's, are the silent, everywhere present condition of no beneficial tiny change. The condition that shapes the grand narrative of reality, one infinitesimal moment at a time. Salam, and peace be upon you.